Hey everyone, today we will be solving LeetCode problem number 232. Implement queue using stacks. Okay, in this problem statement, we have to implement a first in first out queue using only two stacks, and the implemented queue should support all the functions of a normal queue, which is push, pop, peek, and empty. Okay, so let's say this is our queue, and we have to implement this queue. Queue is having properties of first in first out, that the element inserted in the queue the first time it is going to be removed from the queue first. So let's say first of all I inserted 1 into the queue, then I inserted 2, then I inserted 3, and then I have to remove an element. I can only remove this 1, and after that I can remove 2, after that I can remove 3. So this is first in first out quality of queue, and I have to implement this data structure using two stacks, which is given in the problem statement. Let's call it stack 1 and stack 2. We can only use these two stacks, and using these two stacks I have to implement this functionality. And for stack, we already know that stack is already having LIFO functionality, last in first out. Last in first out, that is, I'm inserting 1, then 2, then 3. If I have to remove an element, I will be removing 3 because it was inserted last, and then I will remove 1, 2, and I will remove 1. So from LIFO we have to implement FIFO. Okay, so here we have to implement myQueue class, where we have four operation. Push operation. Push operation means adding element to my queue. Pop means remove the element from the queue and return it. Peek, return the element at the front of the queue, like the element which will be removed if I call a pop operation. Empty, whether my queue is empty or not. Okay, it is an important design question and has been asked in the companies Amazon, Microsoft, Apple, Goldman Sachs, Oracle, and so on. Okay, now let's have a look on this example. Let's just take two stack, because we have to implement the queue functionality using two stacks. And first command is myQueue, that is initializing my class. So initializing class means initializing these two stacks. Okay, that is done. Now let's move to the push operation. Push operation with value 1. It means we have to push 1 onto the stack. Where do we push? Let's keep this stack 1 as a primary stack and push the element into the stack 1. Let's say I have pushed 1 into the stack 1. Now I got another push operation. Okay, so where do we push this operation? I have two options. If I can directly push it onto the top of the stack, or if I have to insert it in the bottom. Because if I insert it in the bottom, in that case the state will look like this: 1, 2. Here, if we have to make a pop operation, I can directly remove it. If I have to peek operation, I can directly visit it, right? So the pop operation going over and peek operation is going over, and empty operation is already over in all the cases. Okay, and but for the push operation, we have to shift all these element and then inserting element in the bottom. So that is a task. So for the push operation, what I can do is I will see later on. Okay, but what if I just directly insert the element on the top of the stack? In that case, when we have to pop it, how do I pop it from the bottom? Will take some processing. And for the peek, how do I peek it from the bottom? Will also take some processing. So here, if I insert in the bottom, peek of pop operation is constant time, peek operation is constant time, and empty operation is constant time. Only the push operation will need some processing. So yeah, if only one operation is need some processing, so I will go with that. So okay, so I have decided that from my stack 1 and stack 2, my stack 1 is primary stack, and here let's say if I have already inserted 1, if I have to insert another element, what I will do is I will be inserting them at the bottom of the stack. So it's the new state should be like this, 1 and 2. So how do I make convert this form to this? So for that, to insert at the bottom, first of all we have to remove all the elements from the stack 1 and then insert that element and then again insert back the element. Okay, now let's say to capture those steps. So first of all I have to remove all the elements from stack 1 to stack 2. So this is our first operation, that all the elements from stack 1 to stack 2. This is my first operation. Okay, now what I have to do is, now the stack 1 is empty, I can directly add my new element into stack 1. Stack 1 dot push. So this is my second operation. And what is the third operation? Adding all the elements from the stack 2 back to the stack 1. Now stack 2 to stack 1. This is my third operation. So what is the time here? Let's make a bigger picture. Let's say in our stack 1, my stack is something like Q. So it should be like this, 1, 2, 3, 4. Here 1 is the element inserted in the last and I am keep on inserting in the bottom. So let's say when I have to insert 5, I will have to insert 5 in the bottom. So what should be the state? This is stack 1, stack 2. After the first operation, what is going to be our state? Our state should be 1, 2, 3, 4, and then I will insert 5 here. So our first operation is shifting all the elements from stack 1 to stack 2. This is my first operation. And the second operation is adding element to the stack 1. This is my second operation. What is the third operation? Reverting all of these elements from stack 2 to stack 1. So what should be the stack? 1 in this case, 5, 4, 3, 2, 1. Okay. Here the push operation is taking some processing. So as we have done some kind of processing, let's capture the time. What is the time here? So in the step 1, we moved all the elements from stack 1 to stack 2, which is order of n time, and adding element to the stack 1, order of 1 time, and now reverting all the elements back to the stack 1, order of n time. So this is the state, final state, and in this is our stack 1, which is primary stack, which is behaving like a queue, because in the push operation it is doing some processing, and overall it is on for the first step, on for the second step, and on again for the third step. So overall it is order of n. So the time is order of n for push operation. What about pop operation? Because we already know that after making some processing, the first element is the element which was inserted in the last. So inserted the first time. So this order is FIFO, first in, first out, like this. So if we directly remove one, it should be the pop operation of my queue. So for the pop operation, it is order of 1. And what about peak operation? Peak operation is nothing just like pop operation, just checking for the top element. So time complexity of peak is also 1. And what about empty? Empty is also 1, whether the size of S1 is empty or not. Stack 1 is empty or not. So in this way, we are achieving the functionality of queue using two stacks, where push operation is the one which is requiring some processing and taking order of n time, and the rest of the operations are taking O1 time. So here in this case, if I have to make m queries, the push operation is going to take m into n, which is going quadratic for multiple queries. Okay, so this was our first approach where we implemented queue using toStack in a simple manner. You can call it a brute force. Let's first implement this approach. After that, we will have a look on the follow-up question where it is asking us to implement all of these operations in is amortized over time. It means that for m queries, for every query should take around over time. So for the m queries, it should not go quadratic. It should be linear. But here our push operation is going quadratic for n queries because every operation is taking n time. Okay, let's first this brute force and then here we will have a look on the follow-up question. Let's try to implement our class. First of all, we have to take two stacks. I will initialize these two stacks in my constructor. Okay, now I have to implement these four operations and we already checked that the pop operation, peak operation and the empty operation is going to take order of one time. So for the pop operation, I can directly return s1 dot pop, and for the peak operation, I can directly return s1 dot peak. For empty, we'll return whether the s1 stack is empty or not. So all these operations are constant operation taking one time. For push operation, we were doing something special, that in our stack we were pushing element at the bottom so that it will maintain the FIFO order. So for that, first of all, we have to move all the elements from stack 1 to stack 2. So while the stack 1 is empty, s2 dot push s1 dot pop. Okay, we have moved all the elements, and then what I will do is s1 dot push, pushing element into stack 1 and then reverting back all the elements. While the s2 is not empty, s1 dot push, what we have to push, s2 dot pop. It is a three-step process taking order of n time. Let's test over sample test cases. Okay, we got some error. We have to pass the value as well, right? Pushing x. On the sample test case, it is passed. If I submit the problem, it is submitted successfully. But here in the problem statement, we are asked a follow-up question that we have to overall make all the operation order of one time on average if we are performing an operation. So if we are performing n push operation, it is going n square in this case. So let's have a look at that approach as well. Here also we have to implement these four operations. In our previous approach, the push operation was taking order of n time and all other operation were taking order of one time. Okay, let's say if we have two stacks, stack 1 and stack 2. So here what I would do is I will take this pop operation and let's say after making 4 push operation, my state is something like this. In the push operation, I'm directly pushing into the stack 1 because stack 1 is my primary stack. Okay, so instead of on, I'm just taking o1 time, just adding to the first stack directly. So while making the push operation pop operation call, what I would do is I will shift all of these operation into the stack, all of these item into the stack 2. So what is going to be the state? Stack 1 will become empty and the stack 2 will become like this, 4 3 2 1. So this is the state after step 1. Now what I can do is, as this is a pop operation, I can directly make a pop operation onto the stack 2. That will be equivalent to my stack queues pop operation. Okay, this is O1 time, and what I would do is I will not move it back here. I will just remain it like this. So here, what is the overall time I took for pop operation? You will say it is order of n because we are shifting all the elements to the stack 2. Now let's say I got a pop operation call again. what do? We'll just pop directly from stack 2, which is O1. So the second pop operation is taking O1 time. And what about the third pop operation? Third pop operation is also taking O1 time. Okay, so pop operation is taking O(n) time for the first time, and after that, until the stack 2 is not empty, it is taking O(n) time. So if we are making n call of pop operation after n push operation calls, it is going to take, for the first call it is taking O(n) time, and for the other calls it is taking n minus 1 time. 1 time for each call. And what is the time taken? Average time taken for each call is divided by n. So it will come around order of 1. So that's why this approach is called amortized O(n) time approach for the queue operation. Okay, now let's say we have one operation left in stack 2. What we have to do, what we will do if there is another push operation call? So if there is another push operation call, we are going to push 5. We are going to push 5 directly to the stack 1. Okay, and if there is another pop operation call, we will pop from stack 2 if the stack 2 is not empty. That is also going to take, fourth pop is also going to take O(n) time, and push is also taking O(n) time. But when the stack 2 is empty and the stack 2 is not empty, we will be making a shifting from stack 1 to stack 2. So this shifting is taking order of n time. And what about peak? Peak is equivalent to pop. So in pop, we are just returning the element and removing it from the stack. In the peak, we will not remove it, we will just return it. So for peak as well, we are taking amortized O(n) time. And for peak also, here we will capture the value in a special variable which is front. So whenever the stack 1 is empty, let's say stack 1 was empty in the starting. So when we are inserting on the empty stack 1, let's say we are inserting 1 on the empty time. So we will also capture this value in the front variable. So after that, if we keep on adding my push operation call, I will know that what is the front value. So let's say n push operation call were made and I added n element in the stack 1, and after that n peak operations were called. So in the peak operation, I can directly return front. But there can be cases that n push operation were called in on of n time, O(n) time each. Okay, and peak operation we are returning front. Let's say now we got a pop operation call. In the pop operation call, what I am going to do is I will be shifting all the elements from S1 to S2. 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. S1 is empty, S2 is non-empty. Okay, now this pop operation took O(n) time. So after that, if I make 4 more pop operation, so those 4 operations are going to take O(n) time each. Now let's say only one element is remaining in the S2. And in that case, I got a for push call for 6, 7, 8 and 9. So 6, 7, 8 and 9 will be added to the stack 1. Let me just say that I am capturing 6 in the front. But here, while having a peak call, let's say I'm having a peak call again. In the peak call, I will see whether the stack 2 is empty or not. If the stack 2 is not empty, I will just return this value. Otherwise, bottom of the stack 1 is the front or is the next peak. So in this way, we are just improving. Push operation is always O(n), empties operation is always O(n). This pop and peak operation is O(n) one time, and after the subsequent call till the stack 2 is not empty, it is O(n). So on average, it is close to O(n) time. So let's implement this approach as well. So here in this case, all of these operations are taking O(n) time, amortized O(n) time. which was asked in our follow-up question. Okay, let's implement this as well. So here in our improved approach, I just initialize to stack, and in the push operation, I'm not doing anything. I was just inserting element into my stack one, and I was also capturing that if this is the first element in the stack one, I will make capturing it into the front variable. So let's say int front is also there. This is also saving some time for the peak operation. Front is equal to, let's say it is -1. Okay, so this is a push operation call. I will see the stack one, if the stack one is empty, in that case the front is equal to x, and x is added to the stack one. For every push operation, I'm just adding element to the stack. And if the stack is empty, I'm also capturing that element to the front. Because if stack 2 is empty, in that case I can directly return the front value in peak operation. Let's say for the pop operation, what we have to do is pop operation. If stack 2 is empty, I will move all the elements from stack 1 to stack 2. If stack 2 is empty, so while stack 1 is not empty, stack 2 dot push stack 1 dot pop. Added all the elements from stack 1 to stack 2. And what I will do is I will just directly return s2 dot pop. Okay. So this is on time for the first time. After that, of all the subsequent call till s2 is not empty, I will be solving it in on time. And what about peak operation? For the peak operation, if stack 2 is not empty, it means the top of the stack 2 element we have to peak. Otherwise, we have front, which is bottom of the stack 1. If stack 2 is empty equal to false. If stack 2 is not empty, stack 2 dot peak I will return. Otherwise, I will return front. And what about empty? When both of the stacks are empty, it will be empty. So return s1 dot both the stacks are empty, my queue is empty. For peak, if s2 is empty, s2 is not empty, then s2 is top element of s2 I can see, otherwise bottom element of s1, because in the s1 we are directly pushing. For the peak operation also s2 dot empty, no, not on the peak, on the pop. If for the pop, first of all, like if s2 is empty, it means no element in the s2, it means bottom of the element from s1 we have to pop. And we are also given in the problem statement that all the calls to pop and peak are valid. It means we don't have to check whether there is any element present to pop or not. These are valid calls. So we have a written code as per that. So moving all the elements from S1 to S2 and then S2 dot pop we can do. Pushing is just directly pushing the element and just capturing the bottom element to save the calls for our peak operation. Okay, let's submit it. Testing over sample test cases. Working fine, submitting the problem. It got submitted successfully. Okay, hope you understood the problem. Thank you guys. If you have not understood the problem, like try to watch the example, try run again for this approach. Okay, thank you guys.